Hey there, and welcome back to part 4 of the easy LeetCode speedrun. So we have another 10 problems here, and let's get started. So given a positive number, return true if it's a perfect square. Okay, this is going to be binary search. Okay, if square is greater than number, that means left equals pivot plus 1, else equals pivot minus 1. Okay. No, heck. Oh, right, we need to also return a false if we didn't find anything. What? Square equals num. Let's see here. Pivot equals left, right, 2. Yeah. Square equals pivot times pivot. If square equals num, return true. So what do we do here? For 14 was false, but this one is not. Okay, that's interesting. So square is greater than the number. Okay, so if this is greater, actually it's the reverse. So then if square is less than the number, then we need to, yeah. Okay, easy to screw up in these binary search when you're doing them in like a minute. Okay, so there's that. Squares of a sorted array given square return square each number in non-decreasing order. So this is going to be so we need to have a 2-pointer here. So left equals 0, nums minus 1. Left is less than or equal to right. Then we need to have an output array. So if left equals right, res.append nums left squared. Okay, if nums left. I think we're just gonna take the greater number first, I believe. Yeah, that seems like it's a better way to do it. Okay. Yeah, so greater than nums right. So these also need to be an absolute value because you can have negatives. So just take the greater number and then res.append squared. Okay, and then otherwise. Oh, and then we need to increment the left here, so. Okay, else append nums right. And then okay. For some reason these are tabbed wrong again, so okay. And we got another one. Oh, it's this one. Ooh. Let's see what we did here. So left, this should be fine. If left equals right, nums append squared. If abs left is greater than abs num right, that should be fine. Res append. Okay. Oh, right. So we need to return it in the other way because we're appending. What do we do? So we have an extra 9 for some reason. That's interesting. So if they're equal, we do this. Oh, I see. Yeah, so there we go. Okay. Alright. Ranging coins. You have n coins. You want to build a staircase. Staircase, k rows. Okay, so hopefully I get this equation right, but I think the number of coins you need to build a row is n times n plus 1 over 2, I believe. So let's just test this. To build a row 3, it would be 3 times 4 over 2. Yeah, so it'd be 12 over 2. Yep, okay. So I think this is binary search again. So left, right equals 1, and while left is less than or equal to right. Same thing. Then we have a res value here. And we can always build one row because we have a coin. So pivot equals left over 2. Then we have coins needed equals, so the pivot is the number of rows, so pivot times pivot plus 1. Okay, over 2, we need to round down, so that should be fine. So if coins needed is exactly n, then we can return pivot because that's our answer. Okay, if coins needed is greater than n, we don't have enough coins, so then it's right equals pivot minus 1. Else we have n is greater, so we have too many coins, so left pivot plus 1 and res equals max res, because we can do this. So okay, and then we should return res here. We have another thing here. Hopefully that's lined up. Nope. No. Oh, Rex. Okay. Alright. So let's do, okay, guess number higher. We're playing this game. Pick a number from 1 to n. You have to guess which number I picked. Every time you guess wrong, you tell you what number picked higher or lower. Predefined API. Number 1, okay. Okay, so this is the same thing where, and then, okay, you pick a number from 1 to n. So this is the same thing where it's going to be 1 to n. And then, yeah, so it's also going to be the binary search. So left, right equals from 1 to n, so 1n, while left is less than or equal to right. Pivot equals, there's so many binary searches in this one, it's pretty nuts. But at least you get to see a lot of them. Okay, so if, what's this API called? Guess, pivot. Okay, so we probably just want to store this, so we don't have to call it multiple times. So result equals guess pivot. If result equals 0, then we have the right number, so return pivot. If result equals -1, our guess is higher, so then it's going to be right equals pivot -1, then the other way. And we should always find a value, I believe, here. We have an infinite loop? I think so. Okay, so let's see what we did wrong here. So, well, left is less than right, right? Result equals yes pivot, result 0. If result equals -1, okay, result 0. So if result is -1, right equals pivot -1. Left equals pivot +1. So if result is -1, your guess is higher than the number I picked. That means, yeah, so that should be fine. Else, left, that should be fine as well. Okay, curious to see the numbers here, because it seems fine to me. And yet we screwed up something. Yeah, input 10, pick 6. Okay, so how is it not changing? That's weird. We did something wrong here. Oh, classic. Okay. There we go. Okay, search insert position, binary search again. So sort, return the index if the target is found. If not, return where it would be inserted. Okay, so first let's handle the case where sorted. Okay, so it's sorted. So if num target is less than or equal to nums 0, return 0, and then so this is if it needs to be before, and then the other case is target is greater than or equal to nums -1. We would need to return length of nums -1. So actually, let's see what happens if it needs to get, no, so it needs to be like length of nums if it's appended to the back. Yeah, so if it's greater, yeah, okay, perfect. Okay, so now that we handled those two cases, now it's a simple binary search again, so 0. Because it's a sorted list, so same thing. And then we're going to have a res as well here, and we're just going to make that -1 for now. Yeah. Okay, so pivot equals, that's right, over 2. Okay, so if pivot, or if nums pivot equals target, then we can just return that. So we can just return pivot. We can just insert in that location. That would be fine. Okay, and then if nums pivot is greater than target, that means we want to insert it before. Wait, no. If nums pivot is greater than target, that means we want to insert the target to the left. Yeah, so then res equals pivot. We want to insert the target to the left. And then we want to, so if we want to return target to the left or right. Right, okay, else left equals. So then if nums pivot is less than target, then we'd want to keep going because we want the one before, yeah. And then here we just return. I don't think this is an easy problem, but it's fine. Okay. What? No. Okay, so I might cut out there. So I screwed up the case that it's only if the number is bigger we can return here. If they're equal, we have to do it at length n-1. So that's okay. Okay, so literally binary search. To target, if target exists, okay, so this is just the same thing again. It's funny. I just took a bunch of problems on a problem list and just took 10 in a row, and they were all binary search. Okay, so let's see here. I guess good binary search practice. Okay. I guess like 10 easy LeetCodes are a good 1 medium binary search or something. So nums pivot equals target. What are we returning here? We are returning the index, yeah. Okay. Pivot is less than target. That means left equals +1, else right equals -1. And if we don't find it, then we just return -1 here. Alright. Okay. Okay, that's interesting. Implement stack using queues. Okay. So let's just make 2 queues really quick. And by queues, I guess I'll use decks. Sure, so we'll just say self dot first q equals deck. Okay. Init, I don't think, does init have anything? No. Okay. Self dot second equals deck. Okay, so we're going to use this first q as the first one. So push is pretty straightforward. So self dot first dot append, we're allowed to append to a q x. Okay, that's straightforward. Pop. Okay, so what we need to do is we need to remove everything from the first. Okay, so while, yeah, I think I know how this is. Okay, so while lang self dot, and then, okay, self dot first is greater than 1. We need to do, we need to pop from the left and push to the right. Yeah, so self dot second dot append self dot first dot pop left. That's Q function. Okay, so now we can do this. So length res equals self first dot pop left, which is going to be the last value. That's going to be a return value. And so if we had like 1, 2, 3, we would. So if we had 1, 2, 3, we would pop them and then append them. So it would append 1, then it would append 2, then it would append 3. Yeah, I think that'd be fine. And then we have to do that basically again. We have to move them for the first one to the second one again. Yeah. Okay, so then while self.second self.first.append self.second.pop left. And so yeah, the same thing. If we had 1, 2, 3, yeah, we would pop them and then it would be the same order. Okay, perfect. Now we just return res here. Okay, top is going to be the same as pop, except, yeah. So it's going to be very similar, except so we're still going to have this res. Now we need to, after we take it, we need to do this one more time to get rid of that, and then we go back. Yes, that should be fine. And then here, just return self.first. When self.first equals 0. So hopefully that works. Okay. Okay, self.second. So what do we? Interesting, it doesn't let us do that. Okay, well, whatever. We can just do temp equals this. Self.first.pump left. Self.second.append temp. Okay, so we can't do that, so temp. And then we have to do the same thing. Temp. It's funny how it let us do it there, so maybe we can do it. We'll go back to this one, actually. Okay, so it doesn't. Wait, what? Temp equals self.first.pop left. What am I doing? Decorate descriptor append doesn't apply to int. Oh, of course. Okay, so all those temps actually would have been fine. Okay, so let's change this code actually to this old code because I just. Okay, so res here, and then we can do self.second.append .first.pop left. It's greater than 1. Yeah. Let's see what we screwed up here. Okay. All right. Can't pop. Okay, let's see here. So while it's left link dot first is greater than 1. Oh, I see. So, okay. So we can't do a top in an empty queue, apparently. We can't do a pop in an empty queue. So if length returns element on top. So did they say 100 calls, only standard operations, the key may be... Okay. So how are we popping from an empty queue in one of these? So let's see here real quick. Pop from an empty queue in this case. And so what should that look like? So we push, we top, we pop, and we empty. So yeah, so these should all be fine. So let's see what we did wrong here. So self.first.appendX, that's fine. So pop. While length.self.first is greater than 1, self.second append, that's fine. Okay, then we pop. While self.second, self.first.append, self.second.pop left. That's fine. Return res and top. While length self.first, self.second append, self.first pop left. That's fine. Okay, now it should be empty. Oh, I see the problem. So we already popped here. So this shouldn't have an... Oh, no, wait. Oh yeah, okay, I see. So this should actually be... This should go to... okay, I see. So we actually need to add it here. First dot append res. Okay, there we go. I think. What is going on? Okay. Oh yeah, because I copy pasted the code. Okay. That's way too much time on this one. Okay, there we go. Be right. Okay, good. Alright, baseball game. Given the scores for baseball game, at the beginning of the game, start with an empty record, given those strings operations. Okay. Record the score plus double or C. Okay, so we just need a stack here. So an easy stack. So for operation in operations, if operation, return the sum of all scores on the record after applying the operations. Okay, so if operation equals plus, then we just stack.append, stack.pop plus stack.pop, and I'm guessing this should always, yeah, so it's always valid. Okay, if or elif operation equals D, double the previous score. Okay, so just copy this. Stack that append select pop times 2. Okay, if operation equals C, and validate removing for the record, so just stack.pop. And then the last case will be anything else. And we want to append this to be an int. Then we just return some stack. Okay. What? You're given a string. I thought it said it was everything was valid. Is it not? However, there will be at least 2 previous scores. Okay, there were always, okay, so what do we, stack that append, stack that pop plus stack that pop, cannot pop from an empty list. So 5-2, did we forget an append? So invalidate the previous score. So we have 5-2, then we invalidate, let's take a look at this. So if I add 5 plus 2, invalidate, okay, it's 5. Add, oh, okay, so this was the mistake. So we don't need to pop here, we just need to do this. So just misread it. Okay, apparently that's still wrong. Does this plus remove anything, or did I screw that up too? So let's see here. Okay, so plus 15. Yeah. So we don't need to pop this either. So that's another mistake. We're not popping, we're just taking them. Okay. Quite a bit of mistakes on these easy ones. To be fair, these are a little bit Tougher than the others, but they're still pretty straightforward. Okay. Valid parentheses. Given these, okay. So what we need to do is we need to see if the closing things are matched. So we can just say opens equals something like this, and we need to match the closing parentheses. Yeah. Okay, so for car in S, if car equals, so if it's an open parenthesis, that should always be valid. Yes, so then we just append it. Append, or just equals. I think we actually are better off having this be an array. Okay, so now, so we don't have to keep manipulating the string. So that'll be that. And this can actually be any one of these is fine. So if it's that, or if it's this, or it is, what's the other one? This. Okay, so any one of those is fine. Else, and then now we have to match. So if car equals this one. Okay, so if not opens or opens dot pop does not equal this. So we're just matching parentheses here. Return false. And then we have two more like this. So this, so it can be this, or the normal parenthesis. So that would be that. That would be that. And now we have to check at the end, return not opens, or opens equals. We have to make sure every single parenthesis was matched as well. So that should be that. Let's see if that's the case. Okay. What? False, true. Interesting. So let's see here. For car and S, so if this is this, open, oh, see the problem. Okay, so this is just car. Okay, now none of them are interesting. Opens that append car. This should be true because we go to this, okay. So if not opens, or opens.pop does not equal this, right? It should be fine, right? So return true if, I mean that shouldn't matter. What am I doing that's stupid? Yeah. Okay, so for car and S, if car is, so let's just print it just in case. And then let's print it again here. I might be missing some spacing thing. Okay. Yeah, so we do have to, okay, why are we printing twice here? That's an issue. If not opens, okay, so for some reason it's not, oh. Okay, and then this should be that. Okay, now it should be good. Apparently, what? Okay, did I miss another parenthesis? Yes, as always. So close, close, close. Oh, right, of course. Okay, now, thank God. Jesus. Oh, and yeah, I just need to get rid of this print. Okay. Yeah, it's definitely easy to screw up on these easies if you're trying to do them fast. Okay, given an integer array nums, integer k, return true if there's two distinct indices. Okay, so there's probably some shortcut, but literally what we're going to do is, so we're trying to minimize this difference, and so we're just going to have a hash map. So locations or something. And then this is just going to be dict int. So for I, range length nums. Okay, if, actually I probably don't want a default dict, I actually want a dictionary. Okay, so if nums I not in locations or locations nums I, so that's going to be the location minus I. The absolute value of the difference should be less than or equal to k, so this is absolute value of the difference is less than or equal to k. Or, sorry, this would actually be, yeah, never mind. So I need this separately. So locations nums I equals I. Okay, and then else if abs minus I is less than or equal to k, right? Yeah, less than or equal to k, then it's true. And then otherwise, we just put in the new location. So locations nums I equals I, return false. Okay, hopefully I didn't screw up this one too. We're on a screw up contest. Nice, okay. Alright, so we finished those. So let's do a quick analysis of anything and then a time and space complexity if we need to. Okay, so it's valid perfect square. So it's pretty straightforward. We know that the square of the number is going to be anywhere from 1 to the number. So we're just doing a simple binary search and we're trying to square whatever pair of value we get. If we get the number, then it's true. If we're over, then we go right, and then otherwise we go left. And so that's just a simple binary search. Squares of a sorted array. So in order to insert these in sorted order, you just have to have a left here and a right here. And then you have to see which absolute value is bigger, and then you can either insert them from the biggest value first or the smallest value first. Because like if this value is bigger than this, if the absolute value is bigger, the square roots of, the squares of both are always going to be positive. So you can just keep going and comparing and seeing which one's bigger and put that in until they're the same number. And if they're the same number, just put that in and then you're done. Okay, arranging coins. So so the formula of how many coins you need for this kind of thing, this is just something you have to know. For this is going to be n times n plus 1, and then this whole thing over 2. So for example, if you have row 3, this would be 3 times 4 over 2, and so on. If you have row 4, it would be 4 times 5, which would be 20 over 2, which would be 10 coins. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Yeah, so this would take 10 coins. So you're just figuring out how many coins you need, and then the number of rows you're going to have is going to be anywhere from 1 to n coins. So you can just set those as a min and max, and then we're just simply putting in a random row using a binary search and seeing are we high or are we low, and then going from there. And anytime we can, so we're also here, anytime we have enough to fill a row, we're saying, okay, put that number into the result. Because that way we can just end like this instead of having to do more checks. Otherwise we have to know, otherwise this wouldn't be less than or equal to, this would be less than, and then you'd have to return one of these, which is more confusing. And so for these binary searches where you're trying to put something in right before a value or right after a value, this is the easier way to do it. You just keep updating the result in one of these conditions, and then you can just have this. Okay, guess number, higher or lower. This is straightforward as well. This is just binary search. And then we're guaranteed to have a target. We're guaranteed to be right eventually. Search and insert position. So there's a couple edge cases. If the number needs to be inserted at the very front, and this is how we check that. If target is less than or equal to num0, then it's going to be 0. And then if the number is inserted at the very back, then it's going to be at position length. Otherwise, what we're doing is we're saying if the number is greater, if the current number we're at, let's say we're here, or let's say we're here, is greater than the target, then we're just going to say we're currently going to be inserting the target here, but then we're going to be shifting this right value to go here, and then we're going to be checking this whole thing. So we're going to constantly be shifting the value we're inserting our target at until we get the value that's to the left of the right spot that we need, just because we're going to run out of possible choices. And then it's the same kind of thing. If we didn't have this res equals pivot in this check, then we'd have to we'd have to not have this less than or equal to. I'll probably do a medium problem that's something along the sort in the future to explain it a little bit better. Okay, so this is literally called binary search for a target, so that's okay. Implement stack using queues. So a queue can append to the right, and it can pop from the left. So let me just show you that real quick. Okay, so yeah, so a queue can append to the right and pop from the left. And so the way to implement a stack, let's say we have these numbers, right, 1, 2, 3, in a queue. So a stack, the functionality is we should be able to see this value, and we should be able to pop this value, and we're appending to the right. So to push, it's the same thing, but to pop, what we need is we need another queue. And then what we simply need to do is if we want to pop, we need to get rid of values in this queue until there's only one value left. So we pop left, insert here, we pop left, insert here, right? So this would be, so this one would get inserted first, actually. Then the 2 would get appended. And now this queue would only have this 3. Then we can just pop this value and save it somewhere. And then we have to take this 1 and 2 and put it back into our original queue, right? So we pop left, append it back in, pop left, append it back in, and this top queue then becomes 1, 2. So that's how you do a pop, and a top is pretty much the same. The only difference between a pop and a top is once we pop this last value, we need to pop it back in. And so what we do is we get rid of these two values same way, and then they go in like this. And then after we pop this last value, then we need to put it into this queue, or we can either put it into this queue, or we could append it after we take all these values and put them back. Either one works. So it's pretty much the same code as pop, with just like one extra line of code. And then empty is just we check the length. So it's pretty straightforward. Baseball game. This is just a normal stack. So you just append numbers, and then if you do have a plus, you take the last two numbers and you add them. And so this is one of the easier stack methods. And so with parentheses, there's a couple of rules. When you have an open parenthesis, anything is valid, right? So it doesn't really matter what you have. As long as everything before that is valid, it doesn't really matter. Like you can have anything, right? As long as anything before that is valid, any open parenthesis would be a valid operation. But then for a closed parenthesis, what we need to do is we need to make sure that, so for example, if we have an open, like this wouldn't be in, I think they actually show you, right? So like a case like this would be invalid because we have an open parenthesis and then we have a closed bracket. So anytime we have a close, we need to check what's the very last open parenthesis we had, and does that match our closed parenthesis? So anytime we have a close, we pop from the list of our open parentheses. And if there is no open parenthesis, then we know we have a closed parenthesis that's not matched, and then we know that's not a valid parenthesis. So we pop, we check is it the right one. If it is, we keep going. If not, we can return immediately. And at the very end, we have to make sure that we have no open parentheses left, that they were all matched. So that's pretty straightforward. And then contains duplicate. There isn't. I think there's like a more optimal way to do this, but literally all we're doing is we're storing the index of every value we reached in a hash set, and then we're just saying, okay, so we're trying to minimize this distance from abs I to i's j. So we're just saying, like, if we have a number that we had before, is it a valid number? If not, we're just going to take the index we had before and replace it with the new index, because we're trying to minimize the distance between the I and the j. So if we ever do hit this number again, then we are way more likely to have a successful solution if our number is farther down this array. So like if we have, say 1, 2, 3, 1, and k is like 2, if we hit a 1 here again, if we replaced this location with this location, now this is a valid solution, where if we didn't replace it, then we would have this, and this would not be a valid solution. So that's why we do that. So we just simply, anytime we hit the same number, it's either going to be an output or we replace the location. We don't really care about this one after we find another one. Okay. And so let's do the time and space complexity real quick for these. And most of these were binary search, so that's pretty simple. Okay, so here this is binary search, so I could probably literally just copy most of these. So binary search is log n. That's the benefit of a binary search compared to a linear search, and then space. Space for a binary search, a default binary search is O1, so we're going to have a lot of these. Squares of a sorted array, this is a two-pointer technique. And so for a two-pointer technique, with nothing special, you're just going to have a big O of n time because it's a linear. And then we didn't make anything extra, so this is, oh, we did make something extra, but usually the result doesn't count. But if they're counting the result as part of the space, then space is going to be O of n. Okay, arranging coins, binary search, so literally this. Okay, guess number higher or lower, binary search. What the? Okay. All right. Search insert position, binary search, binary search, binary search. Implement stack using queues. Okay, so our time for init is going to be so we can say init is O of 1. And then you are probably going to want to have times for each of these functions typically in an interview as well. So for push is going to be O of n. No. Push is going to be, push is going to be O of 1. Push for Q is the same as stack. Okay, for pop, it's going to be O of n depending on the number of elements in our queue because we have to pop them all out and then we have to take the very last one. So that's going to be O of n, and then top is going to be O of n, and empty will be O of 1 because we're just getting the length. And then space init is going to be O of 1. Push is going to be O of, well, for this is just more like, I think we're not going to have space usually for every method. So the space is going to be O of n, and that's just the number of items we have in our stack at a time. So the O of n is going to be the number of items we have in our stack, the most number of items we have in our stack at some time, which will be, if it says it's 100 calls into it, then we can, if we for example get push 100 times, and this would be 100 and so on. Okay, baseball game is a stack. So it's just the number of operations. So if it's 1,000 operations, so if it's 1,000 operations, then for every operation we're adding something new. So it's just going to be, so time is just going to be number of operations. So of operations, every operation should be constant time, and then space. We do have this stack, right? And that's going to be a number of operations as well. For every operation, we're adding something new onto the stack. Valid parenthesis. So we do have, so time. We are going through the parentheses one at a time. So that's going to be O of n. N is the length of the string. Space is going to be O of however many. So if it's the length of the string, it's going to be n as well, right? So we have this list of parentheses and we're appending onto it. So it's going to be O of n. Contains duplicate 2. We have a hash map, and then we're iterating through everything at big O of n. This is just like kind of like two sums, so O of n time. And space is going to be O of n as well for the hash map. Okay, so that's everything for these problems, and I'll see you in the next one.